Yeah, hello everyone, and we are very sorry we're a bit late due to some technical issue. And welcome back to our third episode of the series, Microfluidics and Business. I've already seen some familiar names, so thank you so much for joining us. And this episode is something that we have been requested a lot to talk about different fabrication methods in microfluidics. And again, my name is An. I'll be the coordinator for the workshop today. And before we get started, I'd like to run through some housekeeping items. This is a recorded session, and we already gathered some questions from your registration form, and we'll start with those questions for all the speakers. And in the second half of the workshop, then in the first half, you can continue to send in more questions. And in the second half of the workshop, it will be interactive. So we might unmute you so that you can speak to our panel today directly. And when you are unmute, if you're comfortable, you can also turn on your camera when speaking. So this is just a very open discussion, and we hope it will be an engaged discussion. And that's it for myself. Now I want to start by introducing our four speakers with us today. Each will be bringing a different perspective on fabrication, from glass, plastic to 3D printing. And first, we have Mark Gilligan. His video is not very good today. If you joined earlier episodes, you might have seen him before. Mark is the CEO of Black Sheep Power, and he has been working on many different microfluidic solutions, scalable solutions. And then joining us, on my screen next to him, I have Tobias from IMT. He's an expert in glass chips. Yeah, he's waving. You can see him. And then next to Tobias, we have Paul from Rapid Fluidics, who is an expert in advanced 3D printing. And next to Paul, we have Madalena, formerly with Stratec, and she will be sharing a lot about injection molding for different applications, biomedicals, and so on. So that's my part. Now, I'd like to ask our speakers the first question. Could you help introduce yourself and also share with us a little bit about what you think, seeing the topics of this episode? Maybe we can start with Mark.
Yeah, so my name is Mark Gilligan. I'm, as Anne said, the CEO of Black Sheep at the moment. And in the past, I founded a company called Dolomite, Microfluidics, and a variety of other brands in what was called the Black Trace Group. That group of companies used microfluidics in many different ways, but we had our own glass fabrication capabilities, but we also designed the first microfluidic 3D printer, which we launched in 2015, which was called Fluidic Factory. We also designed and made a number of different devices which were injection molded by a variety of injection molding companies around the world with different feature quality. So I think overall, it doesn't matter whether it's glass, it doesn't matter whether it's prototyping, it doesn't matter whether it's production at sort of 100-fold, 1,000-fold, or 100,000-fold per year. I kind of have got a perspective on it all, and I think it's a very interesting topic of how to approach the general subject space of which materials to choose and which fabrication methods to choose. So I'm very interested in the topic anyway. Maybe Tobias, you could go next.
Absolutely. I'm Tobias Bauert. I'm the Chief Sales Officer for IMT Microtechnologies. IMT is a foundry for microstructures on and in glass. We do that for many different industries, much like a silicon wafer fab would do for the CMOS industry. But we don't do that for CMOS applications. We do that for optical and photonic and microfluidic applications. So I guess I'm not here for my expertise in sales. I'm here for my expertise in microfabrication on and in glass. I was working for a glass company before I joined IMT a long time ago, and I worked in the IMT engineering department for 6 years, developing products and processes for general microstructures on glass. And I was for 3 years the group lead for our engineering group for microfluidics and life sciences applications, developing microfluidic chips together with our customers to bring that to, well, production state. So I guess I am the glass person today, and I can't deny that. I'm a glass person through and through. I don't think there is such a thing as a best fabrication method. I think all of there are pros and cons, and I think in the end, and I hope, well, we'll see how this hour goes today, but I think a lot is defined by the application, what you're trying to do in the end. And this will define the material you need, and this will also, at least in part, define the manufacturing technology that you'll need. But as I said, I'm a glass person through and through, and I like microlithography, I like etching. This is where I'm at home at.
Thank you. Paul, do you want to go next?
Yep, can do. So I'm Paul Marshall. I'm founder and CEO of Rapid Fluidics. We've been running for about 5 years now, specializing in using resin 3D printing to create microfluidic systems, predominantly prototype level, but also looking to batch production. Yes, I'm a big fan of 3D printing, as you'll no doubt guess, but we are looking at other manufacturing processes as well. We're looking into ways of using thermoplastics as a stepping stone towards injection molding, for instance, and as a way of getting to batch production. There's lots going on there. My background is mechanical engineering. Prior to running Rapid Fluidics, I ran the engineering for a diagnostics company developing a disposable microfluidic cartridge for a portable point of care molecular device system, and it was that process where we came up with the idea of pushing the boundaries of 3D printing to get true rapid prototyping. Subsequently, I saw the opportunity to offer that as a service to a global customer base, and we've been going ever since.
Very nice. And when you think about the topic of today, what comes to your mind?
Choosing the right fabrication method. It's, as Tobias said, no one system is perfect. Everything has their strengths and weaknesses. The strengths of 3D printing are, three-dimensional geometry and sheer speed. There are limitations, however, and there are many times when we have to just refer inquiries and refer customers on to other manufacturing companies. And I think the great thing with the industry is, because each sector, each business has its strengths and weaknesses, on the whole, everyone is happy to collaborate. And it's a great situation to be in.
Yeah, that's very nice. Mada, do you want to start?
So, hi, I'm Magdalena Schimke. I have a background in biology, so I'm a cell biologist, aging biologist, and regenerative medicine professional, where I did also my PhD in. Through that, mostly through the approach to regenerate certain type of organs, I also came into the field of microfluidics to really scale also products that are helping the regenerative purposes in the medical field. Mostly in the bone regeneration was my original topic when I started out with this field. To see the other side of the coin, I joined the company Stratec, specifically the sub company Stratec Consumables, 5 years ago, pretty much exactly 5 years ago, as a basically consultant for biological questions, but also as officially as business developer, and also dealing with innovations in the field of applications in the area of microfluidics. But of course, I also had to deal with the technology Stratec provided, and they are focusing on injection molding processes to really force and support the large scale up of microfluidic devices, also instrumentation for clinical diagnostics primarily, but the side I was engaged with was really focusing on the injection molding of polymer-based microfluidic chips. And then, since Tobias said he's the glass person, in this case, I will be the plastic person as a surrogate, mostly since the company I worked for the last 5 years really dealt with highly transparent polymers that are being used for biomedical applications, primarily clinical diagnostics. Regarding the topic of today, I think the questions that came up are extremely important. I'm really happy that we also record that, because I would have have saved a lot of time if I had a recording and a discussion available like that the last couple of years, because many of the questions being posed and asked already beforehand are really, really important for the decision-making tree of each and every company that collaborates with a service provider for 3D printing, for glass manufacturing, for injection molding, whatsoever. And we are there, I guess, to help our clients to decide what is their right path for their current status. So I think the questions are very well, and I'm excited to discuss about them.
Thank you very much. Thank you all for your introduction. And I think we already have a very nice group of speakers today. Also, and the first question that we received is, this is, I think, will be an open discussion among all the four of you. So our audience wants to know, when choosing a fabrication approach for a new device, so if they're thinking about making a new device, what are the things, maybe top 3 things that they should consider before making the decision for what fabrication method to go with? So
I'll take that first. Sorry, my video really is very bad. But anyway, yeah, I think the thing about it is that the first question is where are you trying to end up? So if you're just in an academic lab trying to publish a paper, the answer is very different if you're making a medical device which has got to be disposable, used once, and be sold for pennies and millions of samples per year. So it's a very different kind of question. So I think the first thing is, where are you trying to end up? And I think I'll try and sort of round that out a little bit, but at the same time, if you're trying to publish a paper, you don't mind if you're spending a few €100, even thousands of euros for making a device just to be able to do the work in the first place and get a result published. If you're making a scientific instrument, you might be happy for the device to cost you €50 to €100, and you're going to make a few hundred or maybe a few thousand of those per year. And if you're going to make a scientific product which has got a disposable device, but it's used by scientists, then you might find you need tens of thousands per year, and you need them to cost single-digit dollars, maybe a few dollars, maybe $10, $15, $20 a year, or each, sorry. And then if you're making a medical device, which actually has to be disposed of after one use, and it might be used for a few minutes each time and then thrown away, then you need it to cost probably $1 or less, and it might be made in millions of units per year. Now, so the ultimate goal of where you're trying to get to matters in terms of what decisions you make at the beginning. That's the first point I'd make. I think that's enough for me to say at the beginning, but I think that's the thing, I think, for me, was the important point to start with anyway.
Yes. So the first thing that you will start with will be how many devices that you need, and then what does the cost look like, and some other requirements.
The cost target, yeah.
Also, as a biologist, I have to add that it's also, of course, very important what is the actual application, because, I mean, at the end of the day, we deal with biological substances and with biological product, may it be a cell, a protein, a fluid, whatsoever. So the material that we're going to use and the method we are going to use also for bonding and those kind of aspects has to really fit to the actual biological question we try to answer. So without that, the whole thing doesn't work. But the business case, of course, is extremely important.
Say as well, more. Please.
I was going to say, in addition to what Magdalena's saying about, there's the concern about what goes inside the microfluidic chip. You've got to consider what's going on outside as well. What's the environmental testing conditions? What temperatures are you running this? Are you doing PCR where you have to cycle it to 100 degrees? Is it running at room temperature? Is it extreme pressures, anything like that? So you got to take that into account as well. So that it's the whole operating conditions. It's what goes on the inside and what's going on the outside as well. Will affect the material choice, and therefore that affects the manufacturing choice.
I find it almost funny that we absolutely agree, all of us. This is truly. I mean, and I have seen this before in panel discussions and conferences. The final goal. What are you trying to achieve? And you need to find out what kind of restrictions does this final device basically pose on that you'll be needing. And then, of course, scalability and cost per unit and prototyping cost and all that comes as well. But I think, and this is the one thing that I would like to highlight, when you're at the beginning, don't look at just the first prototype. Look at the goal that you're trying to achieve further out in volume. What are you trying to do? What kind of restrictions will come and haunt you later on in the project? And I think this is something you should not forget, even in the beginning.
Yeah, just one thing to come back to the point I was making about the end goal is I've seen people who focused on making stuff out of glass at the beginning because they happen to have access to a glass fab in a university somewhere, and therefore the startup goes on with a glass device. But ultimately, they can't use glass. I've seen one startup that failed because they needed to process in the hospital systems that they were selling into. They had to be able to process everything through the furnaces in their basement as waste once they went in, and glass would not be processed by the furnaces and turned back to black dust, basically. And therefore, they failed to succeed because they had a glass device in their ultimate product, because the hospitals just wouldn't allow them the doctors to buy the product because it couldn't be processed by the waste systems. I've also seen people who actually have used 3D printing at an early stage thinking that's going to be fine, but ultimately later it didn't work out, although it was fine for manufacturing at that earlier stage. You couldn't fabricate those devices in injection molding or glass later because you were making features that were impossible to replicate any other way. And 3D printing wasn't a viable method for scaling up manufacturing, both from cost and reproducibility perspective. So all I'm saying is every methodology has its extreme strengths, but if you don't know where you're going, or you don't decide on the basis of where you're going, then you can end up with getting tripped up by it. But I would say that there's no question that glass is the most inert material. I mean, of all the materials we're talking about, there's no question that glass is the most inert. So therefore, if you want to have a material which doesn't interfere with your assay or whatever it happens to be, as Magdalena was saying, glass is always the best material for not interacting with your activity, but it doesn't mean it's always the best material for making the final product, and therefore it doesn't necessarily mean it's the right solution. But yeah, so I think it's just focusing for me on the end goal to start with is important anyway.
Thank you. It's good to have everyone agreeing with each other in the first question. So I'll bring up the second question where we might see different opinions. So the question is, what do you see as the biggest strength of the fabrication method that you are working with? And if possible, could you also suggest a certain application for that fabrication method?
Let the others go first because they're championing one particular method, and then I'll see if I've got anything else to contribute at the end.
Tobias, do you want to go first? Because Mark has just promoted glass.
I'm here for microlithography and etching, but this goes along with glass. So it's not just a fabrication method, but it's the material as well. And I mean, while to say you always have to use the material that is right for your application. I think we've covered that. And you shouldn't use glass if you should use plastics. Now, this being said, over the past years, I've seen a lot of projects in glass microfluidics, and there are certain very compelling reasons why a lot of people choose glass. And I mean, this is not now an order that should be ranked from top to bottom, but what you always, or in a lot of cases here, is optical properties. So this can mean optical clarity, this can mean a transparency at certain wavelengths, this can mean autofluorescence, and a lot of other optical applications. Mark said it's a very inert material, so chemical stability, if you're dealing with very harsh chemicals, can be very advantageous with glass, and therefore with microlithography and etching, especially if you're dealing at elevated temperatures. And one particular thing that comes with microlithography on glass is added functionality that you can include in a microfluidic device in glass. So you can include other thin films that have been structured on the glass. So this can be used for electrodes or optical apertures or optical filters and a lot of different things. And the core strength of microlithography is the extreme high definition structuring of these thin films on glass. So this helps a lot, and in some cases this can really be the game changer, because you cannot do that in a different way. I mean, I've heard people talking about, well, prototyping cost, it can be very advantageous too, but in the end, I mean, it really depends on what you're trying to achieve. There are other things that vote for glass, like, but this is very application specific, like the rigidity of glass, or maybe the transition temperatures. Something that I hear often is the intrinsic hydrophilicity. So clean glass is just intrinsically hydrophilic. So the applications with aqueous solutions you almost have no bubble trapping or no issues with that, because, well, the aqueous solution just hugs the walls of the system. I mean, in the end, nobody chooses a method or a material just for no reason. But these are some of the very compelling reasons that I've seen in the past why people are rooting for glass, or have to decide for glass in the end.
Magdalena, why don't you go for plastic?
Yeah, I'm here. I'm here. It's just the internet connection is a bit bad. Can you hear me? Yes, now it works. Uh-oh. Can you hear me?
Yeah, we can hear you.
Perfect. Okay, perfect. So yeah, so of course, I mean, Tobias is absolutely right of the points that he stated before. And sorry if I may repeat myself, but of course, I mean, in principle, it's a matter of the application of what material is actually useful and what not. I mean, one of the major advantages of using polymers in that sense is, of course, when you combine it with injection molding, is the scalability. Because if it's about the price pressure of a certain product, of course, polymers are unmatched, because they're just the cheapest and fastest manufacturable process once the equipment around is actually established. The investment of the equipment and the equipment that you actually need to get to that point is relatively high. So this is the downside of the whole story a little bit. But in terms of also applications, as also Tobias pointed out, is that you can also modify the surfaces of the polymer with films, with coatings, with metal coatings, with glass-like coatings. So you get actually closer to the chemical environment of a glass device. But then, of course, things like rigidity and so on and so forth have their challenges in polymers. However, there is in the meantime a very wide variability of polymers available that can be really tailored and adjusted to the certain application, to the price point, and to the manufacturing technology, and also following not only applications but also the manufacturing methods, and also integration of sensors or those kind of things. So this is also a very important point, but still, other than that, I think Tobias has addressed most topics that are very important on that setting, on that question.
Thank you. And then Paul, please go on.
So, okay, so with 3D printing, I mentioned earlier, there are two huge advantages. Yes, there are a lot of disadvantages. You know, the material, the resins that we use tend to autofluoresce. There can be issues with biocompatibility. So there's very much limits as to what's applicable. It's something that we know about, and it's something that we'll happily tell customers that we simply can't, you know, make the parts that they need if that's the application. But the positives will often outweigh those negatives. Three-dimensional geometry. You can make massively complicated shapes that you simply cannot make any other way. That's no good if you're looking at scaling up to injection molding 1 million parts a year. If you can't actually make a tool for it, there's no point. But if you don't need to do that, then you can incorporate, you know, if you need a helical cell sorter because that's what your research tells you, that's great. If you want a replica of anatomical vasculature geometry for organ modeling, we can do that. You know, there's a lot of things you can do. And the other thing is speed. You know, Magdalena said, you know, injection molding is fast. It is. You can churn parts out by the second once you spend weeks and thousands of dollars setting up the tool. With 3D printing, you can get that part within a few hours. You know, the ability to try multiple iterations of prototypes, assuming it's suitable. If you're happy just flowing water through just to see how a mixer works, if you're doing a pneumatic control system, you can try a design every single day of the week for weeks on end. Within 2 weeks, you've got 10 different designs. And that ability, the savings you get from prototyping with 3D printing, it's massive. There's other great things you can do with this as well. Embedding components, so we can mix and match, so you can go for the high precision glassware, the high precision thermoplastic components or electronic components, and embed them within 3D printed parts, so you can actually create a hybrid system. Obviously there's challenges, nothing's easy, but it can all be done, and it works really, really well. So there are limitations, as I say. Some cell culturing experiments are tricky to do, even on certified biocompatible materials. Some are absolutely fine, but for the majority of assays, the majority of simple water systems and pneumatic systems, then there are no limits there on 3D printing.
I think I think that for me, I'm just thinking about what everybody's saying. I mean, I do agree with what everybody's saying, but I think that the key thing is, on a given axis of measurement, I think you can rank them on one. I think you can rank each technology against one another on each metric. So if you think about the speed to get to the first part, there's no question 3D printing will be fastest. In my personal experience, glass microfabrication with etching would be second, and injection molding would be last.
Yeah, because you have to build the tools, but once you have it, it's pretty fast.
No, exactly. No, but assume you haven't got a tool because it's a new design, then you have to build the tool, and that takes time. So whereas for 3D printing, you don't need a tool; you just upload the CAD data and you print it out. And whereas a master for etching can be made very quickly if you want to. So it's actually not a difficult thing to start making glass parts quickly. If you look at ultimate cost per device, if you make a lot of devices, there's no question in the end, probably injection molding will be the cheapest. Also, it's not necessarily true that glass will be the most expensive, because if you make enough small devices on a wafer, the devices can be quite cheap, actually. If you can fit 10,000 devices in a wafer, then even if the wafer costs 10,000 euros, each device only costs €1. So you can still make a lot of devices. And the 3D printing is the one which is sort of most linearly flat. I mean, it's just, probably, Paul, you don't save much money on device 1,000 over and above device 10. They're going to cost about the same each device to some extent or other. It won't reduce in cost dramatically over time as you make more of them. If you look at pure technical performance of material, glass is the highest performance material because it's very inert and it's incredibly precisely fabricatable. It's optically transparent. It doesn't autofluoresce. And I think the 3D printing materials are probably the lowest performance materials because they're very, very constrained in what you can use, unless you're going to do FDM or something else other than but then you've got very low resolution. You can't do tightly resolved features. And then the injection molding, you can use some materials which are better in their performance, like COC or COP, but they're still not as good as glass in most circumstances. So what I think the main thing about it, really, I'm saying, is that you can't rank each method against each other in an absolute sense, but within a variety of parameters, you can rank them. And therefore, it comes down to, for your given need, when you look across which the factors matter to you in your application, you can work out which fabrication method might be the one that's going to be best for you in that situation. That's the main point I'm making.
No, absolutely. I agree. I mean, only with the one thought that also came to my mind before is also a topic that we address regularly when it comes to injection molding, is also, even if you go very high up, the reproducibility and the variability between the parts is very low, the reproducibility is very high. So this is something that might not be relevant for all of the devices, but when it comes to really small features, as we talked about, very low micrometer to nanometer features, I think, because there was asked about some benefits, this is actually application technologies that is a very, very beneficial when it comes to the injection molding technologies, when you do the mold and the tools in very high quality as well. So reproducibility, and combined with the speed, combined with the modification options that you have, gives plastic in that sense a bit of an advantage for many applications, not for all, but for some there is.
I think there might be some debate there, just to try and defend glass a bit here, just to remind everybody I don't have a favorite material, but I think glass might be better than plastic when it comes to reproducibility of very, very small features. I don't know, Tobias, you're the glass man, you might think so too.
Yeah.
Yeah, absolutely. I mean, I agree with Magdalena that you can achieve very high reproducibility with plastics. I think if you really go to the extreme, I mean, injection molding, you can do wonderful things today, going to sub-micrometer precision. If you use microlithography, there's almost no limitation. If you think in terms of a silicon wafer fab, and you can almost do the same things on glass. But what needs to be considered, and maybe this is what Magdalena was hinting at, is that manufacturing glass components is a batch process. You don't produce a chip by chip, but you always produce at least one wafer or a batch of wafers, right? And so you will have minimal batch-to-batch variations. And this needs to be considered. This needs to also be considered in your quality control. You need to make sure that from batch to batch your variations are okay. But on the other hand, you don't have any tool wear. I mean, the lithography masks, they just don't wear. If they wear, they're just broken. So over time, your tolerance regime will not shift dramatically. It will shift from batch to batch. Usually this is not a huge deal. It can be something you need to consider if you go to the extremes, sub-micrometer precision. But usually this is not an issue. But this is something that you don't have usually if you're churning out millions and millions of injection molded parts, I guess.
Thank you so much. So I think the answer that I hear repeating again and again is that choosing the right fabrication method is depending on the application. So from our audience today, if you have any specific use case, a specific application that you want to discuss with our speakers, please leave your question in the chat box, in the Q&A box, and then we'll address them. And before I go to the second part where you will speak with the audience, I have a question, the last question. So now imagine that you have someone who's trying to set up a fabrication method and they already made a decision on the method that they want to use. And for example, if they decided that your method is the method of choice, is there any like common mistakes do you see when once people already decided on that method, but then on the way of setting up that method, there might be some common mistakes that you have seen so far?
Yeah, so if I might chime in here, this is a very important question as well. I mean, ideal case, the customers and the clients or the team that intends to bring a product to the market or device to the market has already made up their mind very clearly beforehand why they choose a certain manufacturing method. I've been working the last 5 years primarily with younger companies or spin-outs from universities, so very scientific-driven groups that have very innovative ideas. So often there's even not a comparison of a similar product on the market in that sense. So this is all very new and all very unknown fields that they're approaching, which is makes the whole thing so very exciting. From the pure manufacturing status, from using injection molding and so on, one of the most common mistakes is actually at some point, that they forget about their smart engineers and maybe material scientists or clinicians even, but they forget about the biology. The second is that they forget about the end users. So whom are they actually producing the part for, and do they have features in their design, features planned on their devices that make the device actually usable for the intended target group? So it may be a manual use, or may be a scientist, may be a point of care, or may be an instrument using the device purely and not it's not going to be in touch with a human. And the third, and maybe the one that I saw the most often in our case, was that people had not informed themselves before what are the financial burdens and challenges when you actually start with injection molding right away. I mean, we discussed before that the once you have the tools, the reproducibility is great, and the price can be very low for chips once they're in 2 dimensions and once they follow certain design criteria. But to get to that point, it takes time. Is for smaller companies or universities, often a large investment. So, and through that time, while we have produced the tools and so on, they don't have anything to show to their investors and maybe not even to their boards, because this thing is in process and it takes months until you get functional tools. And sometimes they think like it's going very fast, but in the end of the day, to finish all the discussions, to get through the real manufacturing status, it takes way longer than people expect. And that's maybe one of the major mistakes that I've seen so far.
I think that the one thing is that's worthwhile basically giving an answer to is, given that I'm the person who doesn't have a fabrication method, that I will suggest, and you guys can disagree with me, to get to your first device, Magdalena, from injection molding, if you have got no tool and you have to make a tool and you have to make a part, you're going to spend somewhere between 50 and 200,000 euros to get to that first part, because actually you can't make a tool very easily for less than 50,000 euros, and some complex tools will need to cost much more than that. So, and then the main thing about it is if for injection molding, if you want, I'm sitting in Vietnam at the moment, we can injection mold things in Vietnam with tools costing 3,000 euros, but we can't do that with parts that have got features in the 5, 10, 50, 20 micron region.
Absolutely.
So the only people in the world that I know that can do very high quality injection molding with the precision required for microfluidics are basically in Japan, Switzerland, Austria, Germany. I don't know anybody in America. So basically, I think basically mainland Europe and German-speaking countries and Japan, basically, if it's really precise. With glass, you can get your first part in your hand. Again, Tobias, you can disagree with me here, but I think it's probably 10 to 20,000 euros to get to your first part, not 50 to 200,000 euros. And also, just from a time point of view, injection molding is probably, by the time you've made the tool and you've got it working, Magdalena, it's probably between 3 and 5 months, I would have thought. I don't know if I'm wrong there, but it's something in that region.
Long. Honestly, it's so with us, with Stratic per se specifically, it's actually at a month, and not go from 50,000 unless you make a special deal, but start with 100,000 nearly. So yeah, you're absolutely right. Yeah.
And whereas Tobias, if you've got a normal customer, then you can probably get first parts in somebody's hand within 3 months, probably, can't you? Whereas Paul, you can get somebody a first part probably for a few £100 in a few days, really, probably. I mean, I don't know, but you can always do that. You might be busy, but you probably can.
Few hours sometimes.
Yes, exactly. So you have to ship it to them. Sending it to them might take longer.
Local customers, we've done same day delivery.
Really? They send you the file and you can drive it over to them, or they can come and collect it the same day.
Literally, yeah, that's happened.
And so the thing is, the cost to the first part is very clear, that basically injection molding will be most expensive, 3D printing will be cheapest, and glass will be somewhere in the middle. And also time-wise, injection molding will be the slowest, and 3D printing will be the fastest, and glass fabrication will be in the middle. So it's kind of the ranking of these things is fairly clear-cut. It's more, this is the reason why I said that we need to focus on the long term, is because if you do 3D printing, but actually it's only going to be a step along the way, because you're never going to be able to survive with that in the long term. Or if you go to glass, but you know you can never use a glass device later, you're going to almost be delaying having to solve other problems. So it can make more sense to not start in the wrong place. But I'd say the biggest problem for me with injection molding actually is, I mean, I love injection molding, but it's basically the first time you get a part off, sometimes it just doesn't work at all, because you couldn't replicate that part in any other way that was quicker, cheaper than injection molding it. And you
Absolutely.
and you screwed up, like, you know, when you designed it, not the fabricator, but the designer didn't quite think through something in the right way, and it didn't behave as they expected when they first got it. And then if you've got to modify that tool and change the insert, Magdalena, it's probably still going to cost you tens of thousands, 50,000 euros to adjust it.
So we collaborate, we work very tightly with the partners. So like Stratic works very tightly with the collaboration partners to ensure that this is actually not happening, because the key is that the Stratic Consumables experience of over 40 years doing that with even the employees, they are partially working there for such a long time. And so it's a longer discussion phase before you get actually started. So before you actually agree on starting producing a mold tool or an insert or whatsoever, you really have a relatively long period of going into the nitty-gritties of everything, into details, and maneuvering through all the likelihoods of failure over the long run. So the company really invests in the consulting on that regard as well. So sometimes it leads to a loop back, and basically customers or clients or partners go back to their desks and redesign the device in order to reduce the risk for manufacturing. So the likelihood of a working outcome is actually higher. And yes, it happens, but it actually, once we engage and once the company or other injection molders as well start, they supposedly know that the outcome is most likely working, and statistics speaks for the success in that sense. So you don't manufacture into the blue, because it's too much of investment for everybody. That's for sure.
So now maybe we can continue with Tobias and Paul.
Yes, absolutely. I mean, your original question was, what do we see as high risk or maybe bad decisions that are made? And for the manufacturing of glass components, I think the biggest mistakes that we see is that people realize they will need to go to glass eventually, but they don't make the step. They just postpone the step of switching to glass. They stick with PDMS, or maybe they do polymer lamination or something like that, and they postpone that to later on in the project. And this is extremely risky, because once you change the material of choice, you change the manufacturing method, obviously, but you change everything else. You change the bulk materials, the surface material, the surface properties, the interfacing, and whatnot. And we urge our customers to do that switch as early as possible. I mean, you can do your PDMS kit and do your quick and dirty prototyping, but once you understand what you need in general, and once you understand it, you will need to switch to glass eventually. We urge everybody to do that as early as possible, because your design does not need to be finalized. You can do multi-iterations on a wafer, you can do multi-iterations like sequentially, and we'll help the customer finding an optimized design, also in terms of optimized for size. So the cost will be as low as possible. But doing that switch as early as possible, this is what I would urge everybody. And these are mistakes that we see from time to time, that we just consulted too late in the project, and a lot of changes need to be implemented too late in the project.
I'll have to agree with the point that's been made about being so fixated on a particular manufacturing style from the outset, without assessing all the possible options. If you're determined to go down one particular route and you haven't considered the other options, without looking at the overall application, whether it's marketing applications, operational applications, whatever the needs are, that's what will drive that decision. And as Tobias says, making the focus on where you need to be as soon as possible is obviously beneficial, but consider all the options before you do that. Other kind of mistakes that we come across are people just simply forgetting about the practical aspects of this. It's all very well designing incredibly small microfluidic chips, because you're moving a single cell from here to here and in single figure micron channels. But you have to be able to hold the thing. You have to be able to connect tubes to it. And sometimes they get packaged so closely together that the interfacing instrumentation or manual handling of things is just completely forgotten. And that's, people are people. If you're expecting users to actually, if it's trained lab technicians, fine. If you're expecting somebody to use this in their own house for doing whatever diagnostics they're doing, point of care diagnostics, they've got to be able to pick the thing up, and it's got to be bomb proof. You've got to be able to handle a thing and shove it in a machine and just expect it to work. So you can't have delicate systems for that. It needs to be sturdy and well engineered and designed to fulfill that solution, which is beyond just the microfluidics.
I think the one point I'd like to add to that actually is that one thing that's really in favor of plastics at times is being able to integrate macro scale features with micro scale features. So putting wells integrated onto a device where there's a microfluidic channel as well. There are challenges with doing so. If you injection mold milliliter scale wells and there is a 20 micron channel underneath those wells, then it doesn't make the injection molding process necessarily easy, but it's possible. And also in 3D printing, you can easily do the same thing. But I think that I've come across projects where people have therefore although they really wanted the performance of glass in the microfluidic world, they kind of compromised because they wanted to integrate the microfluidic channels with wells. And actually, you can make hybrid material devices effectively where you have a glass chip with the microfluidic channels in it and with larger scale features in a polymeric injection molded part, and integrate them together in a way that is cost effective, because you can end up having almost the best of both worlds. So I agree completely, Paul, that if you've got teeny weeny little parts with the microfluidic channels in them, they're difficult to handle. But if you embed them in a polymeric part, which interfaces by nature its design to the microfluidic features, then you can sort of almost have the best of both worlds in some cases. So I'm just trying to point out that
absolutely.
Sometimes it doesn't have to be a black and white, this or that. It's a bit of this and a bit of that, which you put together to make the right answer.
I agree with you, Mark, but honestly, at least from my perspective and what we have seen so far, this is great, and it works on like if you have highly skilled people who assemble the pieces and really careful, but like for having a product on the market and scale it accordingly with the same quality and so on and so forth, all the challenges this comes up, it's still extremely hard up to non-possible to achieve. So there is things where people asking a lot of questions will integrate, for instance, just not even a structure, but just a simple microscope glass slit into a injection molded cartridge that is made of plastic, and combining this, but simply due to the shrinking factor of the material, it will always have leaking problems and major issues in reproducibility on that regard. So I wish this happens more often, and I think technology will go that way. We have just not seen yet so many products where this has been integrated successfully, like for Protein Simple, where they introduced the Western blotting and have metal pins in a injection molded part and so on. So that's one success story eventually, but also very often just on the paper, and very, very often these been marketing products so far, and not really integrated into standards testing or scientific element. But anyway, a point was very important for me also to finish up this a little bit from my side, is that we have to combine the technologies anyway, and have to collaborate and work way more together using those different materials when it comes to sensor topics and so on and so forth, but also, for instance, using 3D printing or to scale, but rather to 3D print a master or insert instead of 3D printing the individual devices. And once you have a very smart 3D printed master, injection molding could also develop in the direction of being able to produce three-dimensional pieces. But you cannot just do the master is the problem in that sense. So that's something I'd advocate and hope technology goes that way, actually.
You know, I think I'd like to counter the point. Maybe Stratec hasn't seen integration of different materials without skill, but I have seen that a number of times now, Magdalena. So it comes down to the skill of the designers, not the fabricators, to design the materials and use the optimal processes. And I think it's actually very achievable, but you need skill and experience to be able to do it, of specifically making hybrid devices, but it is definitely achievable. But it doesn't mean you can put a bit of glass into an injection mold tool and put molten glass all over, or molten plastic all over it and have it survive. That's not what I mean. So that's very different kind of thing. Injection molding, insert molding, that's different. That's very difficult. Good. There are some questions here, Anna. I think perhaps we could talk about some of those things, because I think there's been some messaging about it, but.
Yes, there have been some questions and also answers, but I also want to invite our audience to speak, because maybe there will be some follow-up. So, Jose, I'll unmute you with video right now. Can you try to speak?
Hi. Yes, thanks. Oh, did it go through? Yes, thanks for unmuting me. I think my question is what stated into the chat, and it's been answered. I was just wondering, maybe if I can iterate on that, for anecdotal tales to that end. Say if you have a specific application experience where you can talk about that price point, that price tipping point. And I understand you would have to oversimplify in order to even come to a hard number. But I guess my challenge to both Paul and Magdalene is, like, can you come to a hard number of, volume per year where 3DP goes under your injection molding?
So what I can say from our perspective in that regard is, so generally spoken, the higher amount of pieces you're targeting on, the lower the price point becomes. And it's a bit of the definition, what is high level manufacturing or what is high scale manufacturing. So at the company, we used to, let's say, consider like 100,000 pieces per year as from that on as a high volume product. But we also have products that we make since 10-15 years that are only at 10 to 50,000 pieces per year because they're just way more complex. So in generally spoken, for us, usually 50,000, maybe 100,000, then 1 million pieces are like breakpoints, and the lowest breakpoint is about 500 to a couple of thousand. The key is always, once you have the tool, reproducibility is just a matter of fine tuning and time. But the longest part will be the tool. But then you can make from basic prototyping rules, you can make a couple of 10,000s. And then when you have to go to a serial product where you need really high quality tools that have different material requirements, it's worth it from, let's say, 100,000 to 150,000 pieces a year on. It is also where it makes a difference, the big breakpoint in costs as well per piece. From hundreds and thousands to 1 million and so on, it doesn't make much difference anymore when it comes to the price per piece at the end of the day. And then other factors chime in, like the yield. The yield is, for instance, also influenced by the original design and the according risk factors that you were taking in the very, very early stage of such a project.
Well, one thing I'd like to say also, just I think that I've seen some examples recently of devices that have been made with injection molding because the perception was that they needed to make thousands of them per year, not hundreds of thousands, thousands per year, and it was therefore going to be the only cost viable way of making these things. But the company developing the product was ending up with something that was actually very complicated. So it didn't end up being one injection molded part with a cover on it. It ended up being about 15 injection molded parts with gluing and fusing together and incredible complexity to get it to work at all. So then the consumable cost of manufacture was over $500 in plastics that were injection molded that had hundreds of thousands of dollars of tooling. Just hundreds of thousands of dollars of tooling, and the part cost was over $500 in the end because
we have projects like that. Yeah, exactly. Yeah.
So the main thing about it was interesting in that case, though. A couple of these cases I've seen where it would have been cheaper if they'd actually ended up starting making a glass device than a plastic device, not because of the fundamental fabrication cost difference, but the fact they could have made it with fewer parts by making a glass part, because the glass part was mechanically stronger and would fuse the layers with the microfluidic channel between glass layers, so they can actually make it more cost effective. And the microfluidic area was only like a centimeter squared. So if Tobias made you a wafer of devices that were a centimeter squared, they're not going to be very expensive each. So therefore you could actually make 2 injection molded parts and sandwich the piece of glass in between, and it would cost you probably less than $100 instead of $500. So anyway, all I'm really saying is that some people's assumptions about costs don't necessarily always quite work out, Jose, because it's like it depends a bit more on the specifics. And I know you understand that it's difficult to answer the question without knowing a bit more, but that's the truth. You need to know a bit more to answer the question really well.
Goes back to that statement about making an assumption about your manufacturing technique without considering all the options. You work out what's really going to be the best thing for you. And the retrospectively, the whole scale up of 3D printing and where you can get to there, we simply haven't done that. The largest order size we've done so far is 200 units, and we're looking for more. We're looking for more options where we can go higher. And if you design for 3D printing, you can then become a lot more efficient with the volumes you can achieve. I've genuinely priced up printing 1 million parts per year of a slide-sized microfluidic chip, and it wasn't insane. It wasn't as cheap as you can get for injection molding, but it was surprisingly not that expensive, even allowing for a fairly poor actual return. So additive manufacturing outside of this world of microfluidics is looking at how it can become a scale-up manufacturing process and a large-scale manufacturing. And that technology is new. Everything's changing week by week. So who knows where it's going to go.
Well, I think, Paul, if in this particular example I was talking about to do with a £500 consumable, it was only going to be made 2,000 or 3,000 times a year. And actually, if it's costing $500, it almost doesn't matter what's being made out of it. You could probably do it in 3D printing for less than that cost per part. You probably wouldn't have been able to make it in one part, probably 2 parts and another film of something. But it's still anyway. I think that they would potentially be able to look at it that way as well. Okay, there was one other question here I noticed, which I thought was a bit interesting. Yeah, it was the one where Alexander had asked about using the glass masters for moulding on, and Magdalena made a comment about the temperature difference. But we have actually, in the past, Dolomite made glass masters that people moulded onto, and it was successful to some extent or other. I mean, as in, they didn't always break, but I don't know, Alexander, whether you've got a comment you'd like to make.
Yes, let me unmute him. Can you unmute yourself, Alexander?
Everyone, can you hear me?
Yes.
Hi, everyone there on the webinar. So it's very interesting discussions ongoing, and my point here was exactly to find the trade-off between injection molding techniques and glass, which is usually being selection between one or the other solution. And what I was pointing out is that ourselves, we are also working on using glass as a master with quite successful results by having created the value chain with other companies going through nickel shimps after the glass to create the tools for making injection molding parts. So it's a way to have glass as a starting point, to have rapid prototyping, but always considering with the same geometry to have eventually the customer, if he wants to go in scaling up later on, the opportunity to go into injection molding technique. So there is room for discussion for different techniques to approach both glass fabrication, but also injection molding. That was my point to take here in the discussion today.
Absolutely. Thank you for that question, and I absolutely agree. And mostly for, let's say, prototyping, what we call prototyping manufacturing, when you go to a couple of hundred to a couple of thousand pieces, there is really, really cool new technology also on the way, and also the option of thinking about using a glass master. The most discussion that we have when you really scale up, you talk about like wear of a master in nanometer area, or even below that sometimes, because we also have to ensure, mostly in the IVD field, of course, to have an accordingly high reproducibility. And again, if the structure are relatively large, and if it's like maybe eventually also relatively low volume, considering it is absolutely worth to think about, definitely. Just from the point on where you go through a really, really high throughput with very low tolerances, which we have, for instance, for the cytobil product that some of you may know for sepsis diagnosis, that the tolerance level is so little that everywhere, everything that you do to the actual original insert, no matter what material at the end of the day is something that we have to take care in very, very great care, because even a slight change can actually make the device malfunctioning. And so it really depends on the application, on the design again, and on the actual number and situation of a product, project, or also a company in that sense.
Yeah, correct. Thank you.
You're welcome. Thank you.
Yes, we have one more question, but unfortunately the time is up. So maybe I'll just wrap up the discussion here today. And this is a big thank you for everyone who's joining, asking great questions, and thank you all our speakers for sharing your insight. And yes, just want to say a few things about the next episodes. This is another episode that is requested a lot, which is what it takes to secure funding for your startup. So if you'd like to join the next episodes, we have a survey now, and you can just we have a poll now, and you can just tell us if you want to join the next episode. We'll send you the invitation. We'll also have a survey about like this discussion today, how you feel about that, or if you have any other question you want to follow up with the speakers and so on, you can fill in that survey as well. And that's it for my part. Thank you again. Thank you everyone for joining, and I hope to see you next time. Thank you to all the speakers.
Yeah.
Very much, everybody.
Thanks for having us.
Thanks.
Bye-bye.
Okay. Take care. Bye.